Good morning, everyone. Professor Kurt here. Today, we're going to dive in and explore the wonderful and exciting world of relative motion and how it can help us understand objects through different reference frames. Have you ever wondered how to describe the motion of one object with respect to another? Or why when you're like on a moving body like a car and you throw a ball straight up and it will eventually come down and chase you, even though you're running in high speed? Well, that is because the motion of the ball is relative to the car and not on the ground. To further explain this phenomenon, let's talk about relative motion.
But first, when we discuss the motion of an object, we first need to establish something to compare the object's motion with in order to describe its motion. To describe the velocity, speed, or acceleration of something, we need to choose a reference frame. A reference frame is a set of coordinates that we use to describe the position and motion of an object. In many cases, Earth serves as our default reference frame. And if we say an object has a velocity, it means it has that velocity with respect to a given reference frame. Consider a person sitting in a train moving at 10 meters per second east. In this scenario, Earth is the reference frame. So, when we say the person is moving at 10 meters per second east, we mean the person's motion is 10 meters per second relative to the surface of the Earth. However, if you change the reference frame to the train, you can say that the person is not moving at all, since he's just sitting. Let's look at another example. Imagine a car and a bus driving on a highway. The car is driving 20 kilometers per hour relative to the bus. From this means we can establish that the car is moving 20 kilometers per hour faster than the bus. However, if we change the frame of reference to the ground, the car's speed would be faster. This is why reference frames or the frame of reference is important, as it helps us describe the motion of an object, and depending on it, an object's velocity might change.
Now that we know what reference frames are, let's head back to our topic. What exactly is relative motion? Relative motion is the motion of one object with respect to another object, and it is a crucial concept in physics. Imagine you're on a train that is moving at 60 miles per hour. If you throw a ball straight up in the air, it will come back down to you even though you're moving at a high speed. That is because the ball's motion is relative to the train and not the ground. This means that even though the ball looks still or not moving in your hand, it actually has velocity. Now, imagine two cars driving along the same road. Relative motion between them is like asking, how fast is one car moving compared to another? Relative motion between a car and the road or earth is like asking, how fast is the car moving with respect to the ground?
Another example is walking down a walkalator. Imagine a man moving 0.5 meters per second in a walkalator that moves 3 meters per second. To him, his motion would only be 0.5 meters per second, as his reference frame would be the walkalator. Imagine what is his velocity to a person outside the walkalator and on the ground. What do you think his velocity would be with respect to the ground? Take note that he is in a walkalator that moves 3 meters per second. Pause the video and try to guess. If you say his velocity is 3.5 meters, you are correct. This is because if you compare his velocity to the ground, you would need to add the speed of the walkalator. This is relative motion in one dimension.
This is relative motion in one dimension. It can be summarized as the velocity of A with respect to B equals velocity of A minus the velocity of B. So now, since we have talked about relative motion in one dimension, let's add another dimension to our lecture. Now, let's explain how relative motion works on a 2D dimension.
Imagine two people on separate boats in a big pond. Relative velocity in 2D is like asking, how is that one boat moving as compared to the other, considering both speed and direction? It's not just about which is faster, it's also about whether one is turning left or if the other is going straight. The difference in how they move is their relative velocity. To solve this, we first must need to visualize the two boats in the pond to be in a plane. Imagine boat A heading towards its destination while another boat, or boat B, is traveling in a direction that is not parallel to the other boat. In this case, the angle at which object B or boat B travels is at an angle. Since the objects aren't traveling parallel to each other, we can't use the same methods for getting the relative velocity in 1D. That's why we have to use vector addition or trigonometry to solve relative motion in 2D. Let's see an example. Imagine two vehicles in a road. Imagine a truck is traveling south at the speed of 70 kilometers per hour towards an intersection, while a car is traveling east towards the intersection at the speed of 80 kilometers per hour. In this case, what is the velocity of the car relative to the truck? Since they're traveling perpendicular together, to solve this, we can just use trigonometry. Let's recall our trigonometric lessons. From our lessons before, we have learned the Pythagorean theorem in which one side is perpendicular to another. And from that, we can derive the formula a squared plus b squared equals to c squared. And using that, we can find out the relative velocity of the car to the truck. So, a squared plus b squared is equals to c squared. So the velocity of the car with respect to the truck can be solved by getting the square root of the velocity of the car with respect to the earth squared plus the velocity of the truck with respect to the earth squared, which would give us 80.0 kilometers per hour squared plus 70 kilometers per hour squared, which results to 106 kilometers per hour. Now we know the speed of the car relative to the truck, but we also need to find out the angle at which the car travels relative to the truck. To do this, we can use our inverse tangents. So, inverse tangent of the speed of the truck over the speed of the car would give us 70.0 over 80.0. And if you use inverse tangent on that, it would give you a result of 41.2 degrees north of east, which means the velocity of the car with respect to the truck would be 106 kilometers per hour, 41.2 degrees north of east.
Oh, so that's how you solve relative motion in both in a 1 dimension and 2 dimension. Now, always remember, while solving for the relative motion in a 1 dimension can be summarized as the velocity of object A with respect to B is equals to the velocity of A minus the velocity of B. While, on the other hand, while solving for the relative motion in a 2 dimension can be summarized through the usage of trigonometry and vector addition. Now, let's apply this knowledge with Vincent for problem solving.
Question 1. Imagine 3 cars on a straight road. Car A, Car B, and Car C. Car A is moving at 120 km per hour, Car B is moving at 70 km per hour, and Car C is moving at 40 km per hour. Find the following: the velocity of Car A relative to Car B, the velocity of Car B relative to Car C, the velocity of Car A relative to Car C.
For our given, we were given cars A, B, and C, moving at 120, 70, and 40 kilometers per hour respectively. Now we were asked to find the relative velocities of car A to B, car B to C, and car A to C. Now from what we can tell, it is a 1-dimension problem. So for car A to B, we have cars A speed of 120 and cars B speed of 70. We would use the 1-dimension solution, so we would just subtract each other's speeds, so we would be left with 50 kilometers per hour. So cars A's velocity relative to B is 50 kilometers per hour. For the relative velocity of car B to C, we'd have to get our speeds of B and C, so 70 and 40, and then we would subtract, so 70 minus 40 is 30. So therefore, the relative velocity of car B to C is 30 kilometers per hour. For the relative velocity of car A to C, we would have 120 kilometers and 40 kilometers. So 120 minus 40. So we would be left with 80 kilometers per hour. So the relative velocity of car A relative to C is 80 kilometers per hour.
Question 2. If rain is falling vertically at a speed of 30 meters per second and a person is riding a bicycle at 12 meters per second east to west, what will be the relative velocity of the rain with respect to the bicycle?
For our given, we have the speed of the rain, which is 35 meters per second, heading downwards. As for the bike, it is 12 meters per second, heading to the west. For what is asked, we are tasked to find the relative velocity of the rain to the bike. From what we could see, the rain is heading downwards, while the bike is heading to the west. From this, we could tell that is a two-dimension question. For our solution, we have to use the Pythagorean theorem. So it'll be square root of r square plus b square. So just substituting these values, we'll be left with square root of 35 square plus 12 meters square. Now this would be equivalent to 37 meters per second. We were also tasked to find the direction of the rain, which is tan negative to the power of negative 1 r over b. Substituting these values, we would have tan to the negative 1, 35 over 12 meters, which is equals 18.9 degrees.
Thank you, Vincent, for the wonderful explanation. Now that's it for us today for our video about relative motion. Now, thank you all for watching, and I'll see you guys in our next video.